Problem number 5 is some data that was collected near San Francisco in 1956. They had a series of storms that caused a bunch of different landslides on the San Francisco South Quadrangle. And so the chi-square test is a statistical hypothesis, and it's basically designed to test. I don't have a pencil with me, so I'm going to borrow a pencil. It's designed to test statistical distribution. So if you had a typical bell-shaped distribution, it would look something like that. And so what we do in looking at that, where we have data, geologic data, we use the equation x squared equals the observed frequency, so we'll call that observed sub f OF minus the expected frequency E sub f. That's a quantity squared. That's why divided by the expected frequency of the corresponding category. So when you do that with all this, you would actually sum up all of these. You had 8 different groups of data. So they actually had, we have here on the northwest exposure, the actual. So if we actually put here the observed frequency were 30, the expected we would get would be 14, and then 24, 14, and so on down the line. And when you do this, you end up getting an x squared value that's something around 40 point something. And what that's telling you is that you're not seeing a nice bell frequency at all. And there's 2 reasons for that. One is rock is seldom homogeneous and isotropic. It always has lineations and partings and joints. And 2, you have structural control. In California, everything has a northwest, southeast trending structure. And so all of the slopes tend to be going southwest or northeast. But southwest-facing slopes have less moisture retention because they get more sunshine. And so if we look over here and say this is the southwest exposure, and I have sun here, I'm not going to get as much water on this side of the slope as I probably get retained on the shady part of the slope, which is where you see all the larger trees. So if I have a large storm that comes in, it might trigger some large landslides on this side, but over here on the wetter side where I have higher antecedent moisture, I'll probably have a greater statistical frequency of problems and failures. So it's real dangerous to do geostatistics with landslides. I think that's what he's trying to just point out to you here. They don't obey the same kinds of things. In fact, when you try to use statistics on storm events, it's very hard to do that because the storm frequency changes every year as we get more data into the data set. And we'll be seeing that as we study surface water runoff processes. But to know a 100-year flood, you'd have to have 1,000 years of records. And we seldom have 1,000 years of records. So we're doing a lot of guesswork on these things. And you'd also have to have non-changing weather patterns, or weather patterns that aren't going through a permanent change in cycle, such as we're experiencing right now with global changes. Thanks. So I hope that helps you. But what I'm trying to do there is just expose you to some of those principles and have you able to use those and be aware of them and aware of their limitations. We're going to go on today and continue slope stability lectures, you should try to have your homework done today or soon hereafter, and then be working on writing assignment number 3. And that's the Walmart parking lot grading problem. And on that problem, you want to be able to do things like lay out what a 3% grade would look like across the parking lot area coming north of the building, and then realize when you cut your cross-section, you're not going to see 3%. You're at some 40-degree angle to the normal of what that 3% grade is. So the grade you're actually going to see on your cross-section is going to be something less than 3% grade. So just a lot of little things like that you only learn by going through the construction and going through all the trouble to do the construction by hand on graph paper. I think it's a good exercise for you to go through. And by the way, if we were designing that same project today, the one thing you would never, ever, ever do is to focus all the traffic going right across the front doors, because that's a requiem for accidents. You always want to bring the traffic in at the far end of the parking lot, park people, and then have them walk in without intersecting traffic. So that particular design is a very poor design from a traffic engineering point of view, but that's beside the point. Everybody goes there anyway, right? Okay. Any other questions before I get started? All right. So today I'm going to talk about recognition features of rotational slumps. If we're out looking at landslides, obviously if we have very shallow slides like this, we can see there's something going on here. There's either some really busy prairie dogs up here moving stuff around, or you don't have to be a rocket scientist to realize something's going on here. And it's fairly shallow. It's in the upper meter or two. Here we got some stuff going on, very, very advanced erosion of a much greater scale. We're actually looking at a scarp right there. It's probably 100 meters high or more. And then over here, we're seeing the typical situation where it looks like we have just a bunch of melted ice cream over some kind of surface, and it's very hummocky. That's the key word in landslide technology, hummocky. Hummocky means it's got all kinds of bumps in it, kind of like somebody that has a bad case of acne when they were teenagers and they have these little pits all over their face. It's just all bumpy. And that bumpiness is not typically a natural thing. That is impacted by these movements on the slope, and you see things like this little isolated drainage here. That's called a sag pond, a place where water is trapped and the water can't get out. If you're seeing sag ponds, it's usually either a fault or a landslide that's causing that to be there. You'll also see a deranged drainage. You won't see the beautiful dendritic drainage pattern. You see a lot of parallel and yoke-shaped or Y-shaped drainages. That's very typical of a landslide terrain. Rotational slumps are the ones we hear the most about in books. They have different pieces that have names here. We have the body of the slide. We have these subservient scarps, which we call minor scarps. And then we have the main scarp, which we usually call the crown scarp or head scarp. So one thing about geologists, they're like medical doctors. They got all these different technical terms for all these different things. And there's a lot of colloquial usage as well. Not as much amongst academics, because academics are really caught up in terminology. But when you get out into the real world, there's all sorts of colloquial terms that are used. Now this is a typical slump, a rotational slump with a flow. Now down here, the toe here and right here is flowing right over the ground surface. And so you may not get as well a developed slide plane on that surface because this is a flow slide. This is a slump slide. Now, I've seen lots of geologic experts get into court and argue for days and days and days whether the failure was a slump or a flow. And the reality is it was a slump flow. But they're getting paid by the hour, so they can argue about this stuff and argue about it and argue about it. And they're both wrong, they're both right. One of the things you want to look for is an arcuate scarp. An arcuate scarp occurs through tension. You have a universal pulling away, you get a arcuate type scarp. Notice that the height of that scarp, the exposed scarp, is greatest somewhere near the middle, near the center of the slide mass typically, and then it diminishes in either direction coming down. Then you have lateral scarps, which are a little harder to follow, and then you actually have toe scarps of sorts here. They actually just call it the active landslide toe down here. In this case, right there, it mowed down about 13 houses. This particular one is La Conchita, back in March 1995 in western Ventura County. And here, in this case, the active head scarp up here was over 200 feet high. So they had a very, very high head scarp in that particular case. And later, part of this head scarp calved off and came down this side and killed 13 people down in this area about 10 years later, in January 2005. Well, if we have a rotational slump, what is going on with this slump? It usually has a log spiral shape. And that was Leo Rendulic's thesis under Terzaghi at the Technical Hochschule in Austria, 1934. Rendulic wrote an article, 1935. It's in German and says the slip surface is not actually circular, it's a log spiral shape, and that's true. And the Swedish guys had approximated it with a circle, and that's pretty close for analysis purposes along the Swedish railways back in the early 1900s. But most of them, if they're pure failures in a C-Fe material, they tend to be log spiral shaped. Something that's pure clay can have something close to a pure circle. It has to have a phi of 0. And the higher the phi angle, the more planar the failure surface is. So the higher phi angle materials like bedrock slides, they tend to have much shallower failure surfaces. Now, if you look right here at the deepest wedge, we're going to divide this up into slices, like the ordinary method of slices homework problem you had in chapter 6. And right here, it was number 4, I think. And right here, you can see that when this water level gets up to this point, about 2/3 of this slice is saturated. It's buoyed. So its effective stress is lessened by that buoyance. And so you have 2/3 of the slice being submerged. Through simple rotation of this mass, right here, you go to a more stable inclination where only half of that slice is now saturated. So this is 15% more stable just in this configuration. And that doesn't count the drainage that's going to occur down here due to dilation. Now, when this thing moves, the slide mass increases in volume. There's no way you can get away from that. It is going to increase in volume and dilate, giving you lower unit densities in slide material. Material that's moved is going to have a lower unit density than the material that hasn't moved underneath it or around it. And you'll also tend to get a lot of drainage through macropores when you rotate. So it goes to a much more stable inclination. So if we look at this in plan view, we'd see something like this. On the fall line of the slope, we'd see some contours coming down slope, and on the same fall line, some of those contours bending up slope. Now, if I saw something like that on a topographic map, I'd immediately sketch in something like this and say, I got a little slump there. And these are my key recognition features for that. Now, this is all a matter of scale and accuracy of the topographic map. Here's the bad news. The topographic maps we have today are made with 1920s technology. About 1920. Zeiss stereoscope with black and white stereo pair aerial photos, and you can't take off the vegetation. And so they're not very accurate if you're walking around the forest with a GPS receiver in the 21st century. In fact, if you're in an area that has very high trees or very high topographic relief and you're taking waypoints going down a channel, sometimes the USGS map will have a channel 40, 50, 60 feet away. It's not real accurate. So we have this old technology maps and this new technology way of locating ourselves. So the way to go is Google Earth. Take Google Earth with you and use that, and have your iPhone with you. So if we look at something more planar, more pancake shape, this is the high phi material. So we get more of this pancake shape if we get a phi angle up above, 40 degrees or something like that, or we just see the soil regolith above the bedrock that's involved in the movement. We get a more pancake-shaped type failure. Sometimes these are deeper, sometimes they're shallower. It just depends. So they're not always going to be the same. But the only way you're going to see something like this is if you have at least 5 contours that broach it in a row, and you don't have real thick tree cover to cover up these little variances. So on a USGS map, which is published at 1 inch to 2,000 feet, 1 to 24,000, what's the smallest feature you're going to see that's a slide? Typically something that's 300 feet long. If it's less than 300 feet long, less than a football field, it's going to be real hard to see on a USGS topographic map. So that's not your answer. If you're flying a site, a job site, and you have this done with 5-foot contour intervals, 2 meter, 1.7 meter, something like that, and you strip off the vegetation, you can pick up all the small slides right down to 40, 50 feet. No trouble at all if you have an experienced person doing the data reduction and doing the slide mapping. So very, very reliable way is to just look at the topographic expression. Now the bad news is the topography changes very, very rapidly. So here is an active slide, little slump block slide. It's in bedrock material. We got a scarp right here at the crown scarp at its highest point, about 22 feet, vertical drop in 1983. 1986, we can already see it's raveling down. 1993, considerable raveling of that head scarp, and by 2001, you could miss it if you weren't looking for it. And that's how landslides are. You won't see landslides unless you're trained in them, you have experience in them, and you're looking for them. So here we are. We're 28 years later, and it's already getting mollified. Now, go 100 years, and it gets tough to see unless you really know what you're doing. You're really looking for them. So 100 years in time span of the Holocene, which is the last 14,000, 11,000 years, that's nothing. That's a drop in the bucket. Doesn't mean much. So beware. Here's that same slide, and I'm sketching here what you just saw. You had a nice clean break on a log spiral shape. You had a nice big scarp, 22 feet high. That's more than a 2-story building. And you had this piece fall in back here in the head scarp, and this fills in pretty quickly. And so you get a little bit of a bump right here, but not a whole lot. And that's where everybody wants to build their house, by the way, right on that little bench right there, right at the head scarp. And when you do a perk test right here, you get wonderful percolation. Head scarp of a landslide perks like crazy. As much water as you pour in goes right down in it. Wonderful place to build a house. LA, that's where they like putting the houses, right there in the head scarp. And that's good for us because it makes work for a lot of people in our profession. Now, one of the things you want to notice there is you have all this very low density soil, colluvium, which recently washed into that scarp. If you go out there and you trench this, it'll become patently obvious to you pretty quickly if you're looking for it. All right, here's some slumps we've mapped on the USGS maps along Crowley's Ridge, where you can see the suggestion of some sort of slide. Here's one with a sag pond on it. You got all these little features here. You could circle them. This is a nice one right here. It's probably seismically induced. But then you'd have to go out here and map them, walk them, and drill them out or trench them out to be sure that's what they are. So all you're doing with a topographic map is just making a target map and saying, here's some things that are a little bit anomalous. I'd want to look at these in greater detail to see what's going on. Well, it turns out the steep side of Crowley's Ridge is just 75% covered with landslides because it's in a very seismically active zone. So there's slides. There's another confirmed slide. Here's one where we're flying over Buford Peak area. This is out near Meeker, Colorado. And this HEADSCARP starts over here. It comes up here, comes around all the way over to here. And this whole thing you're looking at here is one big, huge landslide complex that has slid down into this valley and pinched the valley off right here. And this flat area where all these horse ranches are the lacustrine sediments of the lake that was formed by this landslide dam. This Flatiron section of Colorado is just covered with gargantua landslides like this because of the volcanic ash deposits in the tertiary volcanics. Ash invariably toughs weather to smectite clays. Smectite clays have very, very low friction angles, typically 2 to 4 degrees, so you get very, very large landslides with them. Here's the digital elevation map of the Buford Peak landslide, and wow, this is right out of a textbook. Look at the arcuate scarp here, I was just pointing out to you. Just incredible. This thing's 2,000 feet high right here. 2,000 feet high. Comes around right over to here. And this whole thing is the body of the slide. And right there is where things were pinched off. This lake built up to a certain depth. And then there was a catastrophic outbreak flood right here that carved this canyon and left a whole bunch of terraces down here that testify to the depth of the water being about 250 feet deep or so when it carved this thing out right there. Now there's another slide right back here. This is also a big, huge slide going that direction. So they're just one slide after another, after another, after another in this area. And just virtually everything you see out there is an ancient slide of some sort. A lot of these are probably a late Pleistocene age. Total vertical relief, 2,800 feet from the top to the bottom, so just under 3,000 feet. 10 square miles of land area, about 20 billion cubic meters, and the sloping flanks have innumerable slide complexes which are smaller. So you have slides within a slide, within a slide, within a slide. You can't count them. There's just hundreds of them. Here's some of the ones we mapped just off the digital elevation model. Some of the biggest blocks here. So you can see it's just a huge mass of things moving around, pushing down one, then another, then another, then another. We call this a retrogressive slide block system. We have one and then another behind it and then another one behind that. And these are just the most recent ones. These are smaller slides within the parent slide mass. Pretty typical. Now, HEADSCARP geometry. What are some of the tricks of the trade that I've learned over the years? Go out to these sites with my kids and I look at these big active HEADSCARPs, and pretty quickly you can figure out some limiting geometry like this, where you measure this side, you measure that side, you can get some idea of the depth of sliding pretty quickly. You don't have to certainly be a rocket scientist to do that. It's a pretty easy thing to do. When the slides get a little more complicated, this block mass starts moving, and you have more than one wedge in here, typically you'll see something like this, then our construction gets a little more complicated. We have to put this back up to where it was when it started, right there, and then come down to figure out the depth of sliding. But when I've applied these graphical methods, I'm always within just a foot or two of guessing where the slide plane is. And I'd like to know where the slide plane is, so when I go in to do my testing right here, I come out with the slide plane in my tubes down here. Now there's another way of doing that. You would auger first and do what's called a probe. And as you probe down, you probe for the slide plane, you find that, and the driller might say, well, I got a slide plane at 31.5 feet. So they say, okay, pull it all up, move over 2 feet. Let's drill another hole. When we get down to 30 feet, 30.5 feet, we're going to run an 18-inch sampling run, or run a 30-inch sampling run if we're pushing Shelby's, 24-inch, whatever we're going to do. But you always want to probe first, and then you can always do this graphical solution first when you're trying to guess the geometry of the slide for doing a preliminary analysis. These are very useful tools. Estimating the depth, the depth to the slip surface. This is a system that Kim Bishop at Cal State LA came up with. I found this to be a very, very reliable system that he's suggested as well, where he actually looks at the volume of the displacement depending on how far this thing has moved. That's pretty easy to come up with when you go out there and you're mapping. And then by using this, you can actually guess what the depth is down here to the surface for a block glide translating slide. It's not a hard thing to do. So that's why I put it in here. It's very, very useful, and it's pretty simple analysis that can be performed. Oops. Another way is if you see a series of blocks going down, and that's not uncommon at all when you have a big bedrock slide. You can actually use this system and add up these offsets and bring this back to back calculate the surface as well. So there's lots of different ways of looking at that. This is called the discrete shear method, and this is where you can add up all the offsets along here and sum those up and then apply it here to get an idea of the depth of sliding. It's a pretty simple thing to do. So, what are some recognition features of earth flows? Earth flows are statistically the most common type of landslide we see all over the planet. So there's more of these than any other one kind. They're typically limited to the upper regolith within active drainages. So they're having the accretion of shallow groundwater moisture in the upper 3 or 4 meters. They're fairly shallow. And here's a nice case because all the trees are gone and you can actually see them, and it's backlit. The sun's coming from over on that side. Sun's coming in. And so we can see a backlit HEADSCARP right here. Little one there. Nice one right here. And this is a swale, colluvial-filled swale that has an active earth flow. This is a little earth flow on a shoulder. You don't usually get as big as slides there. And then here's another one. The next ravine over has an active earth flow. Now these earth flows never move all at one time. That's one of the great myths that you get out of too many college classes with professors who haven't worked on a lot of slides. Typically what happens is you'll have one section move 1 year. 7 to 15 years later, the middle section will move because the toe's been cut away from that one. 7 to 15 years later, this section, the head section, will move. So you have 3 different movements, 3 different times, and 3 different portions of the slide. That's about the simplest scenario I can paint for you. That would be the simplest one. They get more complicated from there. So if I was to draw a picture, a cartoon, a block diagram, here's what my block diagram would look like. And now notice in the block diagram, I have increasing soil mantle as I go down slope. And as I get into a colluvial-filled ravine, I have a lot more colluvium in the middle of this ravine than I have on the edges. We call these edges the bedrock ribs. We talked about those before, remember, with the debris flows. So there's a bedrock rib. Over here's a bedrock rib. A shallow debris earth flow complex developed on the shoulder. A deeper one developed along the axis of the colluvial-filled bedrock ravine. Now, how many little earth flow events going on here? 1, 2, 3, 4, 5, 6, 7, 8, 9, a dozen. That's about minimum. That's real world. We call this a coalescing earth flow complex. All earth flows tend to be coalescing. This one, we have deeper, more material, and we can see 2 really good, well-developed lobes here. And we also see a drainage coming up, and then the drainage splitting here and going up either side of the feature. That's a dead giveaway. Now here's what an active earth flow looks like. We got a little one coming down here. There's the toe of it right there. We got a headscarp here. It's about 12, 15 feet high. And we got another lobe coming out right here that's active. And we can see that one's coming out of this area, and this headscarp's about 25 feet high. So this one went out about, 300 feet. This one went about 200 feet. And then we have a road right here, and the county wants to come in here and put a high-speed highway right here, expressway. So they call me up and they go, Rogers, I got a little bit of landsliding here, kind of on the fringes of where we want to build our highway, and the boss wants you to come out and look at it and kind of bless it, and we don't think it's a big deal. We don't think you have to drill a hole. We don't think you have to, well, what can you do for $5? Can you? I said, for $5 I can go to Taco Bell and buy lunch, I guess. That's about all I can do for $5. But these guys they don't want to hear about any kind of problem. Okay, this is still a typical client. So you got to decide whether you're going to take this date or not. It's kind of like one of those dating game things, Gorgeous woman, 25 years old in St. James wants to meet you. You got to decide. Am I going to take this consultation or not? Yeah, so you're getting it now. Okay, all right. So I go out here, and I'm looking at this big bulge right here. That looks like a big pregnant belly to me. Does it look like a big pregnant belly to you? Well, I got 5 kids. I've seen pregnant bellies, but that looks like it's got the twins in it, or the quadruplets. Anyway, so I get the drill rig, and where do I go? I go right out of here onto the woman's belly, and I drill. And 90 feet of slide debris. That's a 9-story building of slide debris. Now, can I build a highway on that? Sure. I can build a highway anywhere. It's all a matter of what? Money. Money makes the world go round, the world go round, the world go round. You know that one? Huh? You guys don't know that one. That was before your time. Anyway, it's all about money. Yeah, so you can put the highway in here, but on this section, we had to use a bunch of mechanically stabilized embankments. We had to do a lot of over-excavation. We had real problems because guess how wet this stuff was? Moisture content was all in the 40s, above 40%. Optimum moisture was 15. So that's a lot of microwave drying you got to do to get that soil dry enough to be able to compact it to something. Yeah, this was very, very low density, high moisture content. Basically what you guys would call junk, mud. Okay, so we talked about, when we're in school, we talk about simple slides that look like this. And every once in a while, those things do happen. I've never seen any, but that's what they're supposed to look like, one slide. And then you can have another slide that occurs because you just oversteepen the hill up in this area, so you can get another slide. But basically, this is what they actually look like. They're coalescing complexes. And here's a real one. There you go. You got the houses right here. How would you like to live right here, right here? I wouldn't want to be there. But anyway, look up here. You have this whole mass coming here. You got these rabbit ears coming all the way up to the top. All that stuff is coming down here. And you got passive earth pressures down here. So if you're going to try putting a wall in here, that's the worst place to put the wall, believe me. Put the wall in up here, but not down here. It's not going to be easy. You got another one up here. It's not quite as active. You got another one over here. Not quite as active. Doesn't come all the way down to the subdivision. So if you get up close to this one, that's this one. A couple months later, we fly over it again, and we can see we got a really nicely developed 2, 3, 4 coming down, and we got a real active lobe right here being loaded, right here being loaded. And when you get down on the ground and you look at it from down here, looking up into this area, you can actually see where the material has just flowed and come down. Now this is all fat clay above the A-line. Fat clay above the A-line ain't supposed to be flowing around with no shear strength. It's got cohesion. It's got intrinsic strength. How can it be doing that? Well, real easy. High pore pressures. See right here? Blowout, 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 blowout. These are conglomerate lenses. These little hard things running through here are conglomerate lenses. Conglomerate lenses are like water trucks delivering pore pressure to you. No charge. They just deliver. And so you have very high pore pressures, and you have high drop here, so you get high head feeding into this thing, and this water feeds down in here and it can't get out of the clay. So that's how come you're getting this kind of vomiting on the hillside type stuff like we looked at last week. We're just kind of, and it's flowing around. Yeah. Now, what are some of the diagnostic patterns you want to look for? Well, first and foremost are divergent contours. If you get some contours going uphill along the same fall line that they're going downhill, you got a problem. Either you had somebody up here trying to make a tennis court with a dozer, or you got a landslide. You're also going to see crenulated contours. What that means is crenulated contours have these funny curves in them, and then they go back to being straight. So you have to ask yourself as a scientist, why do I suddenly get this change in contour and then it goes back to its regular pattern? So if you have an isolated crenulation or just a whole series of crenulations, you want to be asking yourself, why is that crenulated? Now, if you have an arcuate HEADSCARP evacuation area up here, you see these curved contours which don't carry on up the slope. That's a dead giveaway. But that's an old HEADSCARP area right there. Dead giveaway. And then if you have isolated topographic benches where you have a bench here, but that bench does not continue up the valley or down the valley, and it's not stratigraphically controlled or structurally controlled. Now there's lots of benches all over the Ozarks that are stratigraphically controlled. So you got to be careful on that one. There's all kinds of benches. But if it's an isolated bench, it's just in this one area, that's usually due to some kind of landslide. So those are the things that would be dead giveaways. Now, you map all this. Does that mean it's a slide? No. It's still subject to your going out there and doing a site-specific reconnaissance to see if there's something else going on. What are some of the other things that can go on out there that I haven't mentioned? Use your head. Use your imagination, boys. I mean, somebody could have been out here doing something. There are other things people could be doing. Maybe they were out there and they had a basement for a root cellar one time. And the root cellar has caved in, and then there's been some erosion into it. You can get features that look similar to this. And then the fill they had out in front of the root cellar place failed down the slope. You could get something that looks similar to this. So you have to go out there and look at it to be sure. But if you're not sure, then you just draw dashed lines around all of it, and you put a big question mark and an arrow on it saying, you know, before you build your $1 million home here, you might want to do a little more investigating. So the keys to identifying earthflows are opposing contours, HEADSCARPs, evacuation areas, necking down at the transition area, right where this is, and necks down, and then it spreads again down here below it. So those are things you'd want to be looking for. Obviously, the better your topographic controls are, the easier these things are going to be seen. With the new kind of LiDAR, using laser light detection and ranging, where you can actually have analog programs that strip off the vegetation, give you bare earth, these things become really easy to see because you can put shading on them from any quarter you want to highlight slopes that are facing north or west or east or south, so on. You can do that very easily with just a couple clicks of the button, and you can really see landslide features. What you'll find out when you look at LiDAR maps is we should be making 21st century topography maps from LiDAR imagery. We would have much, much more accurate topographic maps. I had places, my first PhD student, Bridget Doyle, she was working on seismically induced landslides down on Crowley's Ridge near Helena, Arkansas. Crowley's Ridge is 240 miles long, so we were halfway down Arkansas, and the ridge is about 300 feet high, and there are trees that are 185 feet high. And there were huge landslide bowls in some of those places. where they weren't even shown on the topographic map, because that particular map, a younger person had made it. There was such high tree cover, they missed seeing those features. You go on the next quadrangle over, and there they would be. Somebody did the other quadrangle, but they were a little more experienced. They actually showed the topographic ravines caused by the landsliding, and were able to see through the trees using leaf-off imagery. So back here, we typically take our geology pictures January, February, March. It's called leaf-off. That's when we do our field geology work too, because we don't have chiggers and ticks and stuff. And so, but even then, with the leaf-off, it's hard to see some of these features if it's a really dense forest cover. You sure ain't going to see it in the summertime. Now, effects of age. Is age going to mollify all this? You bet. Age is the great camouflage. So if I have something that's 10 to 100 years old, it can be pretty simple to see there's something going on. If I get 100 to 500 years old, it gets a lot harder to see. If I get over 500 years old, I need a Ouija board and a Bible. I mean, I'm just not, this is really tough. I mean, I don't know. That's going to be a hard one. So the older they get, the harder they're going to be to see. Here's a typical example of a coalescing earth flow complex. This whole slope is a place that just keeps calving off slides, and then they become earth flows. The debris keeps getting remobilized, and these are like big mud glaciers coming down on this road down here. So when you look at the topography of this site, it looks something like that. And you got a lot of really sharp crenulations in your contours, and so you end up getting this Cincinnati sausage slide map, I call it. It looks like a bunch of sausages with all these arrows on it. And that's because these things are all real active. And you can see pretty sharp definition of them here, probably 20 slides. As this system gets more and more dormant, it's going to look like this. And if you map that same thing, you'd be lucky to have something that looks like this. So you're not going to get anywhere near the tonal definition if it's dormant versus what you get if it's active. But this could go to that in one season very easily. And so that's kind of scary. So when we map slides, generally what we're doing, we're only catching the most recent and the most obvious stuff. We're probably missing 3/4 of what's really out there. Ouch. That's kind of like being a doctor. Somebody comes in, you're going to see what they got right now. How are you going to tell what they had 15 years ago? That's all masked. It's going to be pretty tough to do, even with their family history. So here's that similar kind of situation. Same place again, where you look at the contours are much more mollified, and here's the best we can do. We can see kind of there's a slide, and there, and boy. And the rest of this we're just going to call it colluvium. So is it colluvium or is it slide debris? If you're working for a regulator, it's slide debris. If you're working for the developer who wants to develop this site, it's colluvium. And I used to get into all kinds of technical arguments about that. And one of the arguments was, well, we trenched it, Rogers, and you're wrong right here. We trenched it, and we don't see a slide plane. There's no defined slide plane. We just got this colluvium on top of a rotten grass layer. I just started laughing. How do you get colluvium on top of rotten grass? Only one way I know of. It's either dumped there by an ancient Indian dump truck, or it was a landslide that dumped it there. But you think about it, you're not going to get a nice slide plane when that all just hiccuped, vomited onto the slope, and just blew out onto the grass. You're not going to get a well-developed slide plane. But is it slide debris or is it colluvium? Well, you have to ask yourself, how did it get there? By gravimetric processes or all at once? Yeah, I think it's pretty self-evident. It all got there by the vomit deposit all at once. That's slide debris. Okay. Hope I'm not ruining your dinner. All right. Profiles of coalescing earth flows. Here's something really disturbing about earth flows. What's that, Dave? Notice how flat the slope is. 6 degrees. Ouch. Tributary moisture. Hardly any. What is driving this? Ephemeral springs. Ephemeral, big college word. What does it mean?
It means intermittent.
Intermittent, yeah. Every once in a while. Those are the things that are going to drive you nuts in life, because the patient comes in and they're not coughing when they come to the office. You go out there, you're looking around and you're going, I don't see any water. Do you see any water on that slope? There's not a tree, there's not a bush, there's not a cattail, there's nothing there. It's a water-loving plant. But this is at St. Mary's College. When I hogged this thing out, there was a spring right there. Little bitty spring. And so this is all clay, and the clay liquefied, mobilized, and moved downslope till it had sufficient drainage, engendered some shear strength, and it stopped. That's pretty typical. Now what you see when you go around the world with earth flow complexes, typically you get one, and then that triggers the next one, which triggers the next one, which triggers the next one. These might be decades apart, they might be hundreds of years apart. But it's real common when you drill slopes out, you see these kinds of features. This one right here, the only one we saw was that one. But when we went to drill it, we found another one underneath it and a whole bunch of them up above it. Here's another one, similar kind of thing. One over another, over another, over another, over another. It's pretty typical of how earth flows work. Now, let's come back to the Appalachian Highlands. Do we have these features? They are everywhere. Hurricane Ivan, 2004, 16,000 slides in West Virginia. One big storm event. It basically failed every highway culvert in the state because it's a lot of warm moisture coming from the opposite direction of their usual storm flow. So if you look at all the record storms on the Appalachia Plateau, they're on the highlands, they're all from hurricanes coming out of the Gulf of Mexico, coming up through Texas, Oklahoma, Missouri, Arkansas, and coming in from the blind side. The normal storm track on the Appalachian Highlands coming in directly off the Atlantic. So you're hitting the mountain range from the dry side with a whole bunch of moisture. You're just overwhelming it. And what you see are these kind of pear-shaped things like this coming around and all this debris. Now, if I came in here like that Contra Costa Road job and I drill a hole right here, I'm going to get 90 to 90 feet of slide debris. That's what you're going to get right here. What this is, it's one little earth flow over another, over another, over another, over the last 26,000 years, building up this toe. That's what all of them look like. These things are all over North Carolina, mostly North Carolina, Tennessee, Virginia, West Virginia. They're just everywhere. And they just haven't been as recognized there because they haven't sliced and diced their hills up and put 17 million people on them like Los Angeles County has. They get more water, and they got just as many slides as LA. They just don't have the population density. It's going to happen, though. To give you an idea, when Hurricane Camille came through New Orleans in 1969, that storm came up through this area, whammed into Virginia, and killed 400 people. Just debris flows. 400 people. And it just didn't get noticed by people because more people had been killed by Camille down on the Gulf Coast. All right, Crowley's Ridge earth flows. These are some of the big earth, go back. Some of the earth flows. Targets. We map there. They're a little harder to do. This one turned out to be a real nice one right here. Probably was reactivated in 1811, 1812. And this complex was a very active complex, as was this one. This one, we couldn't find evidence of recent movement on. But the other three that we targeted, we did find good evidence on. All right. What are some recognition features of landslide dams? Landslide dams are a huge engineering problem, the one that I've worked on the most in my career because these do the most damage downstream. They do much more damage than a 500-year storm event. In most places, we design the drainage infrastructure for a 25-year, 10-year, 25-year, to a maximum of 100 years for clear water runoff. We don't design for, you know, 1 billion tons of sediment. And that's what you get when you have a landslide dam. When you have a landslide come down and block a watercourse, it's a very temporary feature geologically. The fine-grained material is going to get blown out of here pretty quickly and leave lots and lots of large diameter stuff behind. And the size of this large diameter stuff and the heights of the strath lines can help you determine how big the paleo flood Q, or quantity of water, was. It leaves behind very nice physical evidence that you can apply the standard principles of channel hydraulics to, provided you put in a bulking factor. This terrace right here is left over from the removal of this landslide dam. So it always leaves a nice terrace, and that terrace always has a steeper gradient on it than the fall wag of the channel. It always has a steeper gradient. So now, what do we see with topographic expression of landslide dams? We see asymmetric opposing contours. Here's contour going downhill, and if we go up the fall line, there's some contours going up the hill. So that's probably a slide. We see isolated breaks in the contours. So you come down here, and all of a sudden the contours get very close together right here, but then they're farther apart over here, and they're farther apart over here. So isolated breaks in contours. We see arcuate headscarps. That's your dead giveaway. Arcuate headscarp is a dead giveaway that this thing has pulled away in tension and gone down into the channel. And we see back-rotated grabens and topographic benches. We see an anomalously low gradient up in this area because it's back-rotated. Now, what do these things look like when you fly around? If you get an eye that's trained, these things are just everywhere. They're like mosquitoes. They're just everywhere. You just have to be looking for them. And what do you see? You see a nice topographic bench. This is where everybody wants to build their ranch or their dream house. You see an arcuate headscarp coming around. You see a channel that used to come right through here like that, and now the channel is bending around the toe and going around the feature. And this area around the toe is steeply incised with a series of rapids. Lots and lots of big, huge rocks. It has an anomalously high hydraulic gradient with an anomalously low hydraulic gradient on the upstream side of the blockage. In this case, the blockage is so massive, the channel took a long time to fill up with water and sediment before it could breach. And then when it did breach, it had insufficient stream power to really cut a very deep canyon. So 98% of this slide is still there, blocking the channel. Here's another one, very, very active one, where you have a channel coming down. It used to come straight through here like this and out over here. And you can see there's a lake right there with a lot of muddy water in it, telling you have dispersive clays. And then there's another series of muddy lakes along here. And this is the blockage. The blockage came down right into this confluence here between these two channels and plugged it. Now, this is a real typical one in that you'll see joint control on this side. See all those linear things? Those are joints. And then we see virgin rupture in tension cutting across the grain like this, coming right down like that and into the channel. And then we see subsidiary scarps, semi-parallel to that headscarp. It's very asymmetric. That's how real landslides are. They tend to be deeper on one side and shallower on another. They tend to be linear on one side, curvilinear on the other. They're a hell of a lot more geometrically complex than you're ever led to believe in school. For instance, I've never seen a large bedrock slide with a smooth log spiral shaped failure surface. That only occurs in some soil mechanics professor's dreams. Doesn't occur in reality. What do I always see in reality? undulating slide plane.
Undulating slide plane? Hell, we can't do that one with stable.
No, you can't do that one stable. It's not easy to do. But that's what's really there.
But that would get you a higher safety factor.
Yeah, it will. It'll give you a higher safety factor. It's not real because the thing's moving. But that's what's really going on. They tend to have undulatory slip surfaces. They don't have just pure log spiral shaped surfaces when they get to be this big. This is a big hunker here. How big is big? Well, this one's got to be probably around 4 million cubic yards, something like that. 4 or 5. Here's one in Colorado, Red Creek landslide. This is a state highway down here. The highway's coming up Red Creek. It gets to here. The creek used to go right through here like that. And now comes way out here, comes around, and then goes on up. Here's the HEADSCARP evacuation area. This is where the slide came down, sliding on a tuff bed, on an ash bed, came down and blocked the drainage. And then it's a very steep drainage, so it probably didn't take very long for this to back up with water and then to break out around the distal edge of it and reestablish some kind of semi-equilibrium in the channel. It's a very, very steep gradient going around this thing. If we look at the USGS map, it looks like that. Now, once I show you what these keys are, it's pretty obvious that there's something going on here, because you see the channel coming around and then zipping out and then coming around and going back, and you see a very different topographic character with the topo lines in this pink area than what you see here and what you see here. Got another slide, by the way, just starting right in there. You can actually see it just starting to go. See that one right there? That's a little bedrock slide. So when you know what things to look for, you see this very anomalous bench. Look at that bench right there. That's incredibly anomalous compared to right upstream and to just downstream. That's real typical of a textbook landslide dam. Now, the problem with landslide dams is you get catastrophic outbreak floods from these. Those catastrophic outbreak floods typically never last more than 12 hours. So they're going to excavate this break. Once they start overtopping, it's going to pick up very, very rapidly. And the whole thing is going to be over in 12 hours. So all that stored water up here is going to send one heck of a flood down the canyon, and it's going to be a very, very highly turbid flood. So it's going to pick up a lot of debris and do a lot of damage downstream. The best thing you do is get out of the way. Secret Springs Mountain. This is one that I worked on with the Forest Service out in the Klamath National Forest. And I'll just go ahead and show you what it looks like. This is the largest one I know of in North America that I've ever worked on. Secret Springs Mountain down here. This is a very, very large complex. Flows into the upper Klamath River. This is another piece of it right here. These are all square miles, these squares. This is another part of it on the other side, which probably, this one probably came down here and blocked the Klamath River. Then a huge lake was formed that was about 100 miles long. And then when that broke through here, you had a rapid drawdown condition which triggered this slide, that slide, and this whole slide network on the north side, which then came in. If you run this today, I got interested in this by, I used to run this in my raft. This is called Hell's Corner, the upper Klamath. The river drops 50 feet per mile here on a river that's normal drop is about 9. So 50 feet in a mile, that is an incredible ride going down this thing. And a very, very large feature. So the flood that broke out of this thing, you can actually see evidences of it when you get down here and start looking from here all the way to the Pacific Ocean. You'll see these discontinuous strath lines, which suggest that the water depths were upwards of 400 to 500 feet initially, and then they peter down to about 75 feet by the time you hit the Pacific Ocean. Now, Pacific Ocean is a long way downstream. like almost 300 miles downstream. So that was a big flood going through a confined bedrock canyon. So how big is this thing? 2,500 feet, vertical relief, about 7.3 square miles, 9 billion cubic meters. So it's not the biggest one. Connor's working on some in the, he has one in the Grand Canyon, it's 30 billion cubic meters, and the one right across the river from it's 20 billion. So we got 50 billion cubic meters between two slides there. But 40-kilometer hydraulic choke, it's one of the largest yet documented. So 40 kilometers of damming. So 40 continuous kilometers where the river was blocked by this slide complex. That's a big slide. It's probably seismically triggered. Here's what the digital elevation model of it looks like. Looks similar to that one I showed you at Buford Peak, where you got this incredibly beautiful active scarp right here. Look at that thing. Looks like it was just excavated yesterday. That's at the head end. That's probably a rapid drawdown induced. This thing dropped about 300 meters straight down. And then here's the main scarp coming right up to the mountain and then coming along like this. And these are secondary slides due to the river reroute. But you can actually see all the slide blocks in here, one block after another after another. So this is real typical when you have a volcanic, stratovolcanic terrain and you have ash flow tuffs. Boy, they're just bad news. All the Hawaiian Islands have these things. And half Oahu slid off into the ocean, half of Molokai slid off into the ocean, and these things go off like 40, 60 miles out under the water. They're very, very large landslide features. Azores are another one. It's the largest landslide you'll probably see in your lifetime in the 21st century. It was when half the Azores slide into the Atlantic Ocean. And we know they've done that before, and they create tsunamis, which then go through the Straits of Gibraltar and probably pierce the Straits of Gibraltar and re-flood the Mediterranean basin. That's happened numerous times in the recent geologic past. All right, what do I use to look at these things? I use Thalwag gradients. Thalwag gradient is the Thalwag is the deepest point in the channel. So if you connect all the deepest points in the channel and you make a profile, if you have an equilibrium condition, you'll see a log spiral decay curve, which means with increasing watershed area as you go downstream, the hydraulic gradient gets flatter and flatter and flatter as you go downstream. If you have some kind of perturbance blocking the flow, you'll see a very, very, very steep gradient. There's my 50 feet per mile right there for 40 kilometers. And then I'll see an anomalously flat gradient in the slack water deposits where the lake was. These are lake sediments that got deposited underneath the dam before the dam, which looked like this. There was a big obstruction right here. That obstruction got removed probably in 12 to 24 hours, causing a colossal flooding downstream. And now today, the stream has insufficient stream power, the river does, to take out this entire blockage. So what it does is it flows on very low gradient in this area, kind of, just meandering around, and then all of a sudden you hit Hell's Corner right there. That's Hell's Corner, and volume, you drop like crazy going through that section right there. So that's a real classic way of looking to see if you have a landslide dam, is looking at the channel profile. This one's 107 kilometers long, and that's a textbook example of a hydraulically choked profile right in here. Now, will you get steps like this in profiles? Yes. You'll get steps where you have major tributaries coming in. So if you don't have a major tributary coming in right at the center of this blockage, then it's probably a landslide dam. You could have something that looks like this if you had a major tributary coming in, flushing in all kinds of sediment, which the main trunk stream doesn't have sufficient stream power to remove. Does everybody understand that concept? It's pretty straightforward. All right. What are some of the recognition features of translational block slides? These are a lot more complicated, so we're going to have to go pretty slow. Yep, I'm going to go back. Hang on. All right. This is the kind of thing I see when I'm doing consulting jobs, different parts of the country. I'll have a channel coming down, have a slight bend in it, coming down, meeting another channel, slight bend in this one, and I'll see these convergent little first-order rivulets coming up, and I see an extended nose up here, extended ridge. This looks a little bit suspicious. These two things are the dead giveaways. If you got one coming up like this and another one coming up like that, this whole mass probably moved a little bit. So I have these convergent drainages, and I have sharp downturns, downslope turns in the contour lines. These are the sharp downslope turns. And that's because this thing's moved over. So this contour comes up, turns, and then comes around, turns, comes around again. Ouch. So that's a dead giveaway. Now, if this thing keeps being eroded, eventually you see these arcuate drainages incising themselves. You get an isolated little peak up here, isolated knob, and you'll get a lot of secondary failures that will slide off the parent mass. Right, here's another one, and move in. And you get these convergent drainages coming up and meeting each other up here at the saddle. So that's a dead giveaway that this little thing, this whole big mass, is actually moving slowly like that. And then it spawns all these smaller slides off the parent mass. We call that a composite landslide because it has all these different types of landslides occurring on the parent mass. And that's actually a lot more common than you might think. You see all these little crenulated contours down here. This is all secondary slope instability problems of shallower slides developed in the parent mass. Now, what typically happens on these kind of cases is the geologist or the geotechnical engineer will come in and they'll see these things. They'll see the more modern, the smaller scale stuff, and then they won't appreciate me at all when I come in and say to them, "Oh my gosh, that's just a little tiny thing compared to this big, huge monster you got here. Have you thought about that?" Now, there's a bunch of these with Three Gorges Dam. They have a lot of these kind of features in China, and they're not too concerned about them because they're going to have water out here, and the water is going to buttress the slope, and that's true, and that's fine as long as that water doesn't suddenly drop for some unforeseen reason. If that ever happens, then you're going to see a whole bunch of these things move. That's what happened to us in Lake Roosevelt behind Grand Coulee Dam back in the 1950s. They brought Grand Coulee up as fast as they could during the Second World War because they wanted all the hydroelectric capacity to run the aluminum twinning twinning of aluminum in Washington State around Pasco and for the atomic bomb project. And then they got to the 50s and they had a period there where they got a lot of dry weather all of a sudden. So the lake started dropping down, and all of a sudden they started having wholesale pieces of the around the lake to start sliding slowly into the lake. It was due to rapid drawdown. And they said, "Well, geez, it's not rapid. We're not dropping it at a foot a day, and we're going like an inch a day." Well, but it's a big lake. And that's a big change in pore pressure. If you're going to go inch a day and you just keep doing it and doing it and doing it for a couple hundred days, that's a couple hundred inches. That gets to be significant. So that's when they had a lot more emphasis started being put on drawdown effects on slope stability. If we look at Crowley's Ridge, these are some of the translational features that we identified that have these isolated knobs that look suspicious. When we went out and looked at these, about a third of them turned out to be actual translational block slides. Not every single one of them, but about a third of them are the ones that we identified as potential targets. And there they are. You can see those isolated necks and the knobs. Now, bedrock slides are always problematic because of the way engineers are trained. Most geotechnical engineers are trained to go out and look at a site and give foundation recommendations. So the focus on their training is on looking at shear strength and bearing capacity. So you come out to a site like this, pretty typical California site, and you drill the site and you got weathered bedrock. And the weathered bedrock has pretty good blow counts using standard penetration test. So you tell them 2,000 pounds per square foot allowable bearing, and you're off to the races. They never consider the fact that this whole thing is a bedrock slide that's moved, and that's why you got this nice bench here that everybody wants to build on. And there's what happens a couple years later. The whole subdivision starts moving. Now what happened there is they came in and they added water and fill. So they surcharged the slide with fill for the houses. The people added copious amounts of water to water their lawns, so they'd have nice green lawns to remind them of Missouri, which they sorrowfully left to go to the West Coast. And down here at the toe, they cut into the slope to create more building pads down here. In this lower area, they didn't get those built before the whole thing moved on them. 2 years later, it looked like this. Now, this one didn't last very long. 2 years is not a very long period. Now, the reason it failed so quickly was when this thing started to move right here, it clipped the water lines. See that? And you clip a water line right here under pressure, it's just filling in this whole slide plane. Got filled in with water under about 80 psi pressure, and so that was the end of everything. And so this is a case where you're not going to see the bedrock slides unless you are looking for them specifically and you have the training to see them. When young in my career, I didn't have the training to see this kind of stuff. I missed a lot of them. I wasn't Mr. Know-It-All. I had my PhDs and everything, but I didn't have the training to see this kind of stuff. If you go back and look at your data on it, there's a lot of little nuances to look for. One of the things here is very low relative density. 78 PCF is not the number you should have for a Miocene sedimentary rock. And that's what these things were. That's a low number for soil, uncompacted soil, in the 70s and 80s. And high water contents. The water content change between right here and right there was dramatic. It was 30 points. You went from a water content of about 37 down to a water content of about 12 right there. So you had a perched water system along that old ancient slide plane. So nobody caught it. They didn't have any geology done on this site other than looking at the USGS geologic map, which doesn't, that's about like, looking at the sky to get the weather. It's not going to tell you a whole lot about what it's going to be like this afternoon. And so they got burned. Translational block slides can be very problematic because of strain incompatibilities between different materials. You have one material that's mushier with a lower modulus, can take a lot more deformation. You put it next to something that's brittle, and the brittle material can't go along for the ride. So rupture occurs right at the brittle, soft interface. In this case, you get a translational block slide on an inclined bedding surface. It comes down, shears across, goes up the other side of the canyon, and then the next one block comes down above that one, the next one above that one, the next one above that one, until you get a more stable inclination and the whole thing comes to a stop. And this piece breaks off and back rotates into this graben right here. So this is a case where geologic structure is driving the whole thing. And in this particular case, they actually repaired it by going in here and tunneling and putting a big reinforced concrete pipe culvert in here and backfilling this in with a big subdrain. This was for LA County Public Works. This was my first job with Dames and Moore out of the Los Angeles office on Glencoe near UCLA back in '74. Dormant, deep-seated bedrock slides. These take a lot of training to identify. And what you're going to look for are things like this, where you have a drainage come up and it wishbones, like that and like that. And then you see this triangular facet right here. And you ask yourself, why am I getting this funny shaped thing here that I don't see here and here? And if you draw a block diagram of it, this is what the block diagram looks like. You have this beautiful house site right here, which, by the way, this is a doctor and a client. He had 40 acres here, and that's where he wanted to put the house. Why? Because that's the only place you could put the house. That's the only flat place. And he says, Rogers, I've heard terrible things about you. I hear you're the kind of guy that takes every house site and finds something wrong with it. And I said, yeah, you probably heard right. Anyway, what happened here, if you cut through the middle of this feature, it's an old bedrock slide, and if you drill a hole down here in the toe of it, you'd go through weathered bedrock and into colluvium and then back into fresh bedrock. If you trench it at the top, which is what we did, we trenched it up here, you find all this soil-filled graben right up here in this flat area where he wants to build the house. So this is just a classic little translatory bedrock slump that slid about 400 feet right out of here, came down, blocked itself. Now, is that an unbuildable site? Not at all. No, that's a buildable site. The problem is you can't do a septic field or leach field on this kind of site. You're going to flush yourself down the hill real fast. So as long as you put in a sealed tank system for your water treatment, you could actually build on a place like that. In this particular case, the most expensive part of the project was the access road to get them up there. So it never got built. That was the reason, not because the house couldn't be built. All right, why don't we take a little break right there for 5 minutes, and we'll come back and continue. Thank you for coming back. Right now I'm going to give you, again, I'm trying to hit things in the lecture that aren't in most of the textbooks based on my professional experience. One of the things we didn't talk about much at all when I was in school was Sturtstroms. Sturtstroms are catastrophic rock slides where you have more than 500,000 cubic meters of material and you drop it more than 150 meters, and through conservation of momentum it loses all shear strength through vibration, even though it's dry, and it behaves like a fluid until it flows far enough and dissipates enough energy that it suddenly sets up, just like concrete. So Sturtstroms are a very real problem. They've been studied in Europe for centuries. Albert Heim was an Austrian geologist who was the father of understanding Sturtstroms. He died about 1935. This is a Sturtstrom that occurred in Buena Vista, Colorado. There were 400 of these Sturtstrom-type landslides in the Great Alaska Earthquake on Good Friday, 1964. And then when we had the Denali earthquake in 2002, there were 200, almost 200 of them, 179 of them. And some of those were very, very large features. So typically they're going to be more than 500,000 cubic meters. Some of them get up into 20, 30 million cubic meter range, not uncommon actually. And they carry and run out for great long distance. Here's one that I worked on with my first master's student here at MS&T, Nick Beckman. And this was one that occurred in 1991 on the West Lost Trail Creek, which is down here. And this is in the upper headwaters of the Rio Grande River. And this is Pole Creek Mountain right here, which is a little over 13,000 feet. The altitude at the base of this Sturtstrom is about 10,000 feet. This is an 8-acre lake that's caught up behind the Sturtstrom, so it's a landslide dam, and this is about a mile from the toe, across the toe, from there to there. And when this thing came down, there was actually a pack train up here that took photographs of it. It came down with tremendous velocity, shooting shrapnel rock into all the trees along here. And this is actually about 11,000 feet. I'm sorry, the toe's at about 11,000 feet, and this HEADSCARP right in here is about 12,400. So about 1,400 feet of drop. If we look at where this is located, like I said, it's in the extreme headwaters of the Rio Grande River, where there's this major fork right here. It comes up and goes around like that. And these two quadrangles are the ones we had digital elevation models made of these two quadrangles, and then we mapped this 64 square kilometer area right here around the slide because the Forest Service had shut everything down up in here. They have a campground and a dude ranch here at the upper end of a reservoir, and they wanted to know if they could reopen it to the public. Well, here's their 10-meter digital elevation models. We're in the San Juan Mountains, which again have a lot of tertiary volcanics, so they have a lot of altered ash flow tuffs and pyroclastic tuffs, Vithric tuffs, and those, about 70% of all the slopes in the San Juan Mountains are massive landslides of one kind or another. So it's just, the place is just covered with large slides. So when we mapped the 65 square kilometer area, this is what the landslide map looked like. You can see it's a very high density of large bedrock slides. Here's where our blockage is. Here's where the 1991 failure occurred. This is a topography prior to the failure we were looking at. And there's only about 4.5 square miles of watershed above that point. This is the Continental Divide. And it's a place where the Continental Divide swings 70 miles west of where it is elsewhere in Colorado, the extreme upper watersheds of the Rio Grande River. And so we don't have a lot of available stream power here, and we don't have a long drainage season to remove debris that clogs channels because we just don't have the watershed area. and we don't have much of a season. When we zoom in and look a little more detail, this area that I've highlighted here is where the 1991 failure ended up being. And prior to that failure, we actually had slides 1 and 2 and 3 in here that were very, very definite translatory slides, and a smaller one right here. And if we look right next door, coming off Pole Creek Mountain, that's the peak of Pole Creek Mountain right there, we can actually see a very well-developed Sturtstrom that came across and blocked the entire watershed in the recent geologic past, and a very well-developed HEADSCARP. This is actually a much bigger feature than the 91 feature. So that was really interesting, and that's the kind of thing you're looking for. When you're doing studies like this, you're always looking for what we call in geomorphology analogs. So if your client's asking you, what's the future hold for this? You can't answer that. How do you know what the future is going to hold? What you have to do is find an analog somewhere nearby that's very similar, and then go to school on the analog and try to date it. How old is it? How is it weathered? When did it breach? Has it breached yet? Etc., etc., etc. The analog's going to be your lab tests to give you your predictions on this. And of course, you have to take into account what the stream power effects are in the analog and the precipitation versus the one you're studying. Now, in my case, it doesn't get any better than to have your analog right next door, because that takes away a lot of the variables. Same geology, same watershed area, same creek, etc., etc. And you don't get that lucky very often. But generally, you're going to look in the immediate area for other analogs. Now, post-failure, here's what it looked like. So we have pre-failure and post-failure topography. This is the precise outline of the 91 Sturtstrom. There is the 8-acre lake behind it. Here is a big block that moved down slope but did not disaggregate, come apart, and blow across the valley. So that's a potential block that could come down and block the valley at some point in the not-so-distant future. But if we look at Pole Creek Mountain, we got a gorgeous scarp up here coming all the way around. We have a feature very similar to this feature that did trigger after the main event, and it came down and filled in like this after this main event came down here and filled in this whole area that you see dashed outline. So that's real interesting. That's an incredibly similar analog, only this one's much bigger. This goes up to much higher elevation than the one we were asked to look at. So that was very, very fortuitous. We look at the air photo taken in 1998. This is what it looked like. You had these little isolated bodies of water all over the place. This is a very rough, rocky surface, and when you walked around on it, it's very hard to walk around on, you could hear roaring water going through the landslide dam coming out here a mile downstream. So you actually hear the water running through it. And nice active scarps up here, which are structurally controlled going that way and joints going this way. Now here is what it appeared that happened. When we look at the photographs taken over here of the failure event, and we go back and we set up on those same places where those pictures were taken, you take pictures at exactly the same place of the pictures, and then you figure out using an electronic distance measuring device how far it is to what's of interest to you. Let's say it's 2,500 feet away. I then take 1 degree of parallax distortion, which would be 25 feet. So I walk over here 25 feet, and I take a stereo pair photograph to go with the one that was taken here in 1991. Now I can take the 2 new photographs and the old photograph, digitize all of them, and I can look at it in stereo, and I can make very precise measurements on those terrestrial photographs. That is an old German intelligence officer trick that was used by their naval attachés in China and Japan and other places. So I've used that particular methodology many, many times on doing forensic assessments. And by doing that, I can make very nice measurements. And what I see in the first set of pictures is I got a slide that's already right here when the pictures start. And the head of that is right in this area, and then a series of slump blocks, retrogressive slump blocks, about 7 of them that look like that, and then one large block up here that's translated, about 100 feet when this thing starts. Now, as this thing started moving, you see the scarps on these blocks start to mollify and disappear as this thing mobilizes into a big Sturtstrom rock slide. And you can see all kinds of cracking off up here. It looks like artillery rounds hitting. These are big, massive blocks that are breaking up along pre-existing discontinuities and kind of grinding against each other and filling in this graben as this big daddy block just translates along. Now, we've moved about 300, 400 feet in this picture. And then, late in the failure sequence, from right here, just the lowermost part breaks loose and comes flying across the valley, just mowing everything down. All these trees, you just see all these trees going, and then of course you get all kinds of smoke coming up like crazy. So it's hard to see any details from that point. And this thing's going about 200 miles an hour across here, and it's just mowing everything down and shooting rocks into the trees over here on the other side. You can still see all the trees of these shrapnel rocks in them, and everything's dead on their south side where this thing came across. Pretty interesting. So when you're done, this is what it looked like when I got out there. And what I can see is that's where it started, that's where it stopped. So it moved, something like 1,000 feet. These are the translated blocks coming down. I got a rock flow deposit here, and then I have a point of detachment here where the Sturtstrom went reeling out over here. So the Sturtstrom didn't really have much vertical drop. What happened here was, it's actually a composite slide because this thing came down and was already had some velocity head on it when it transitioned, or part of it transitioned to a Sturtstrom. So it wasn't a classic start out and the whole thing came down as a Sturtstrom like we thought it was when we started the project. Here's how you can take digital elevation models and manipulate them in 3D. There's that big block that came down that moved about 1,000 feet. So that thing was up here. It moved down to there, and you got this big graben sitting there. Then here is the slide debris all over the place, sitting in here. That's the distal front of it. This is where we would camp, right here, the distal front of it. This is about 30 feet high. And then here is the one off Pole Creek Mountain. And you can see this channel hasn't had sufficient stream power to excavate any of that. What's happened is this filled up until it was high enough that the river could flow around that one and then get back into the channel. So we were able to tell the Park Service, man, this thing is going to be there for a long, long time before you're going to have any major problem with it, especially in the summertime. And if we look at the hydraulic choke in this channel is just gigantic. So here's the prehistoric Pole Creek Mountain slide. Here's the 1991 slide. You can see equilibrium gradient is way down here. This entire channel from its confluence upward is just completely choked with slide debris. It's just incredible. So not a place to get too concerned about all of this stuff coming out. You just don't have sufficient water there to move a great deal of material. So the bigger the tributary watershed, the much bigger a problem you have. So if you have a major river like Gros Ventre slide in 1925, which was up in Wyoming. That one got blown out 3 years later. A huge flood. We had Madison Canyon occur in 1959, also triggered by a magnitude 7.4 earthquake, 7.7. That one is a much smaller watershed, so the slide block's still there. And what the Corps of Engineers came in and lowered the channel about 40 feet to provide a natural spillway, and it stabilized itself. It's been that way for the last 50 years. But Gros Ventre had a much larger watershed, about 1,600 square miles, so it got blown out pretty rapidly. All right. What are some recognition features of lateral spreads? I was brought back to Missouri to look at landslide hazards. When I first got back here and started talking about lateral spreads, everybody looked at me like, what are you talking about? What is a lateral spread? Well, lateral spreads were first recognized in Missouri, believe it or not, about 100 years ago. And when they were looking at the 100th anniversary of the 1811-1812 New Madrid seismic sequence. Seismically triggered slides can be very, very deadly because they happen without any warning. You aren't going to see anything on Weather Channel about it, ahead of time like you do with a hurricane. And when they occur, they move very rapidly, and people don't have time to get out of their way. So they typically cause a lot of property damage and a lot of life and limb damage. Here's 1912. Myron Fuller, working in Missouri in the upper Boot Heel, in the Boot Heel area in the upper Mississippi embayment. He actually drew this picture, and he noticed that when he was adjacent to channels, to major channels like the St. Francis River and the Black River and the Mississippi River, back behind these channels he would see these graben structures. And he opined that the depth of the openings was not usually very great, probably being limited to a hard clay zone that was down here, 10 to 20 feet. But they extended very much below the water level, but not probably over 25 feet. And he realized that this graben structure that dropped down here was due to this block moving towards some void out here, the void being the river channel. So lateral spreads were first recognized right here in Missouri, and back in 1913. Well, they kind of got forgotten about in the professional literature till we got to the great Good Friday earthquake, May 25, 1964, in Anchorage. And here we saw enormous tracts of land, up to a cubic mile of material that failed in various blocks that slid into oceanic areas and sounds. This is Bootlegger Cove, and it actually slid on a sensitive silt, a discontinuous layer of sensitive silt. This is the Turnagain Heights failure, the one you see the big picture of outside my office. If you come to my office at 157 McNutt, there's a big aerial photograph of this one because it had 600 homes on it. And they're rebuilding it right now. They're actually redeveloping this and putting houses on it because they're hard up for real estate in Anchorage. But this failure was a series of horse and graben blocks laterally translating along these discontinuous silts, because you get very high pore pressures in these silts, which were sensitive because they aren't through-going, so they don't have drainage. Well, how could you rebuild on something like this? Well, that's very easy. You just put in stone column drains. That takes care of the problem, and the silt lenses are gone. They've been taken away in the failure. So lateral spreads are a very big issue to deal with. If we look at these big, huge failures that occurred that affected downtown Anchorage, over on the other side of the peninsula, we had these huge grabens going through the downtown area that were a mile away from the waterfront over here. And these were very, very large failures that occurred by liquefaction, causing shear strength loss along some discrete stratigraphic boundary underwater over here. And then you got these big grabens that, of course, cause a lot of property damage and break all the buried utilities, and everything moves out. And this surfaces here can be almost dead level, very, very flat. The big problem you had in New Madrid and in Alaska was duration. You got to realize, we talk too much about magnitude. Peak ground accelerations don't increase once you get above about magnitude 6.4. What kills you in geotechnics is duration. Duration, duration, duration is what's important. So once you get above mag 6.4, your PGA value's going to probably peak out. You're going to start getting plastic deformation, and each cycle of loading, you're just driving up the pore pressures, and you start getting stuff like this happening. Now, how long was the shaking in Alaska? 2 to 4 minutes. This makes the San Francisco 1906 earthquake look like a midget. That was an 8.3. This is a 9. It's up 8.4, 8.5, depending who you talk to. You got to remember, an 8.7 is 250% bigger than an 8.5. It's a logarithmic scale. So you start getting up into these kind of earthquakes, where they're large subduction zone earthquakes. They have very long durations. Each equivalent cycle of loading, you're going to start seeing trouble. Usually you don't see trouble till you get 4 equivalent cycles of loading. Mag 5.5, 5.7 and above, you start getting ground problems. When you start getting out there at 12 equivalent cycles of loading, you're going to see all kinds of liquefaction problems and see things like this. So it testifies to long duration of shaking. Very tough to go out and analyze these things. Now, Horst and Graben complexes are pretty common in lateral spreads. You'll have some discrete layer down here that gets softened and loses strength, and as you have things starting to slide along that surface, typically only 1 to 4 degrees, you'll start getting these Horst and Graben type blocks. And this is really important. And this has to have somewhere to go down here. There has to be some kind of void or valley or lake or something down here for it to move toward. And they're very large tracts of land. So keep this sketch in mind. Because when I came to Missouri, nobody had ever seen this thing. It was like, where'd you get that? Where, that's I've never seen anything like that. Well, it's pretty common actually. So what are the likelihoods that we have these things here? Well, you need to have confined horizons. That's a key word. Confined horizons, saturated sands, silty sands, or non-cohesive silts. So you can't get pore pressure alleviation naturally. So you're going to be adjacent to channels or some other natural depression. And the margins of Crowley's Ridge, where the channels within 3/8 of a mile, you see these things just everywhere. Adjacent to sweeping turns of the major rivers and levees and banks of drainage ditches. So here's one they had excavated called the Holly Ridge site, which they thought, this had happened just before I got to Missouri, the summer of 2000, and they were trenching the Holly Ridge site, which was a quarry on the east side of Crowley's Ridge, down near Sikeston, just north of Sikeston. And here we had Peoria loess, and we had these faults all over the place, and we're seeing like 9 meters of aggregate offset in the Holocene. Wow, that's a staggering number. That's that's a scary number. If you get back from it, these are my sketches down near Holly Ridge. If you get back from it and you look at it from a large scale point of view, what you see is you probably have lateral spreading occurring along some kind of surface down here, and you're seeing this Horst and Graben type of sequence, which these are all getting mapped as separate faults. And they're not actually faults that are through going and carrying for miles. They're localized features tied to a lateral spread that goes back to here and moved out here a couple meters and is really marked down here. And then this fills in with a Peoria loess that gets reworked by erosion, and voila, you get that same kind of feature. But you have to have seen it in some other part of the world. Now, when I'm working in a lot of other countries, especially third world countries, this is one of the big problems I have, is their geologists haven't been out of that country or out of that prefecture they work in to see these kinds of things in other continents. Being in the wealthy country, we're very fortunate. We get to go out in all these earthquake reconnaissances. I've been out to 16 different earthquakes, and every time I go on one of those trips, I see things I haven't seen before. I learn new things, and I find out how much I don't know, which is a healthy thing to do, especially if you've got too many degrees. You want to get out and realize what your limitations are. And the more things you see in other parts of the world, the better trained your eyes are to catch these things in a new place, wherever God settles you. So here's another one of these features down on Crowley's Ridge. Here's the pancake part that liquefied and went out into the river. And then here are these Horst and Graben blocks that tend to get left. This gets mollified pretty quickly because it's completely disaggregated, and a lot of it gets re-excavated by the river down here. But these Horst and Graben blocks are very nicely preserved up here, and you get this arcuate shape coming around on them. Turns out one of these down near Advance, Missouri, is the largest lateral spread in the world. We've now documented it 26 square miles. Goes into the East Fork of the Black River, and it's just a colossal feature with a big 12-meter high scarp coming around, just a beautiful arcuate shape. Well, here's one that Bridget looked at that we found down near Helena, Arkansas, right near where the St. Francis River flows into the Mississippi River, just a couple of miles upstream of that point. It's a large arcuate feature, comes out, and you can see the graben across this section, which is classic with lateral spreads. And we went down and did some geophysics work on that, and it looks like this kind of a feature. Here's that graben feature in the dark gray. These are these arcuate scarps coming back all the way back to here. That's the graben feature. This is the HEADSCARP. And then this whole thing continues all the way down here to Langell River right here, which is a major tributary of the lower St. Francis. The last tributary comes into the St. Francis before it meets the Mississippi. So all of this stuff moved, and that's over a zone of about 5/8 of a mile. And so lateral spreads, typically you'll get a graben feature in this area. That's what that one looks like. This material moved over into the channel. It liquefied along a discrete horizon right here. And then you get a retrogressive series of slump blocks, sliver blocks, which have less and less distortion the further upslope you go. And that's what this one looked like. Looked just like that up in that zone. So pretty amazing material. This is caused by rafting of this material down into the channel. And then these cusping is regression of the HEADSCARP. And then you have the main HEADSCARP being way up here. All right. What are some of the field identification things? You'd look for saturated, cohesionless soils capped by low permeability. That's how you build up pore pressure. So that's the worst condition. Proximity to adjacent channels or depressions. You have to have prominent evacuation grabens because of the block movement. So you're looking for these big arcuate features. And then step topography is typical of these retrogressive blocks going back. And then sand dikes with liquefied material are the most common distinguishing feature. But not all sand dikes are caused by earthquakes. Everybody thinks they are, but there's other things that actually cause sand dikes, not just earthquakes. You can actually get them from just conventional landsliding. Well, lastly tonight, I want to end on talking about what some of the new high-tech tools are for identifying landslide features. This actually shows the digital elevation model that we used where we wrapped the aerial photograph on the digital elevation model and then turned it, rotate it, and we can actually fly by our landslide. We can look at the lakes here. Here's all the subservient, subordinate lakes all over the place, these dark features. But you can actually, looking at it like you're looking at a photograph, and the photograph is vertical, and the topography here is a digital model of the topography. So this is just using ArcGIS about 8 years ago. And you can see what a powerful tool this was for visualizing. I can turn this thing in space and look at it from any angle. I can turn the artificial light anywhere I want to back illuminate things that are like cracks and fissures and scarps, like right up here. These are the very active scarps up at the top, which were pre-existing discontinuities that are exhibited up, that already existed up there. And I can see very easily see the spatial limits of the feature. They show up very nicely. So it's amazing what tools we have out there today. The one that I got most excited about back in the mid-'80s when I was an intelligence officer, working back in Washington, D.C. was synthetic aperture radar. We put a lot of money into this at that time for treaty verification for the Strategic Arms Limitation Treaty, SALT Treaty, SALT 1 and SALT 2. We found out with SAR radar, it had an incredible ability to see through clouds and woody vegetation, up to about 4 inches thick. And the Soviets built all their warehouses in those days out of wood, so that was nice. We could see what they were putting inside their warehouses. And this is looking at a debris flow feature over in Norway during the dry season, where you could, this synthetic aperture radar is from a satellite, and that satellite is scanning from 70 degrees down to 10 degrees. So you can see very slight little bumps and grinds in the topography are very much magnified and show up very clearly. So to see distinguished landslide features, SAR is just incredible. So you can also use side-looking aerial radar, or SLAR, does the same kind of thing. SAR is done from space, and the image resolution and density will control the scale of the mappable features, such as these debris lobes. But this is incredible compared to conventional film photography, which you have all sorts of limitations with clouds, with particulate matter in the air, with seeing through the vegetation. Here you're stripping all the vegetation off, and you're seeing the bare earth picture. So synthetic aperture radar, very powerful tool. The one that we're seeing being used more and more all over the United States, a lot of states have done the entire state now, is LIDAR, which is light detection and ranging using a laser. The laser is out there rotating, picking up 15 million pieces of information every minute, and as it flies along, you're going to pick up things like fault scarps that had never been seen before in places like Payne Run, Virginia. Nobody thought we had a fault scarp running underneath the trees in Payne Run, Virginia, so they ran a LIDAR survey of it, and nobody even believed it then, by the way. Then the USGS sent Jerry Wazorek and some other guys out here from Reston. They went out here hiking through the woods, found the scarp, much to everybody's amazement. We didn't think there was any active seismotectonics in Virginia. So bare earth assessment has incredible potential for landslide mapping, but again, it's always a matter of scale. We call this posting. How often do you put posts in to get measurement points? If you're putting them in every meter, you're going to get a very high resolution. If you're going to map an entire state at 1 meter posting, that's going to cost a lot of money and have some very large, many terabyte type files, but you're going to get a lot more information out of it. And it's very useful for environmental assessment to map change. So that's where it's being used in places like Los Angeles County. They've done the entire county, both with LIDAR and with other techniques even, with interferometric synthetic aperture radar, INSAR. This shows some of the early LiDAR work by the USGS back in the early 2000s in Seattle, Tacoma area in the Puget Lowland. They picked up an active fault coming across here called the Toe Jam Fault. And when they went in and looked at it in more detail, it was just incredible east-west scarp. Again, right here near a major metropolitan area, never been seen because it goes through a very densely covered forest, the dense forest litter. Nobody was looking for it, so nobody saw it. That's a real common problem in a wooded terrain. So this has completely rewritten the seismic risk assessment for the Seattle-Tacoma area, because we realize it's a much more active tectonic area than we ever dreamed. We have these small tear fault transform features, as well as the big, huge, deep-seated magnitude 9 subduction features off the coast, which last moved in 1700. And so 210 years ago, we don't know how often they move yet, but when they move, they're huge earthquakes. And we don't even have an idea yet on what the recurrence frequency of these much smaller features are, but it's certainly more often than once in 1,000 years, most likely. Now, topographic algorithms are what I use. I feel they allow a rapid screening of large land areas. You might combine them with things like neural networks to create artificial intelligence program to delineate these hot spots. The accuracy is always going to depend on the scale of the digital elevation models and the quality of the digital elevation models. And it's going to supplant stereo pair aerial photography methods for looking at potential landslide hazards. That's already happening in California and North Carolina, Oregon and Washington, where they're doing a lot of landslide mapping. Limitations need to be spelled out on the maps. Obviously, you need to recommend site-specific investigations be employed to determine if there's really something there. Otherwise, the property could be considered condemned. This is a big problem in California. Whenever they do a geohazard map, like liquefaction potential or landslide, they always get people trying to sue them. So they have to have a very good government code section that has an exclusion for cause of action because you came out with some sort of hazard map that said, well, according to our reconnaissance work, it looks like this place has a high propensity for having that hazard. That doesn't mean it has it. It means you need to investigate it if you go to get a building permit application or something. That's all. We're not trying to go around and condemn people's property. What we're trying to do is keep people from being killed unnecessarily, especially children, people who can't protect themselves. So recent USGS landslide products. One of these is a debris flow hazard map over here for San Mateo County, a landslide incidence map for San Mateo County. These are the kinds of products that are only going to occur in areas where there's political pressure to do them. The black dots are historic landslide occurrences. The red areas are areas of prehistoric land slippage indicated from aerial photo assessment. So these kinds of products are really undergoing a tremendous metamorphosis right now because you have all these geographic information systems that you can put and deploy, and you can put different factors in here and combine those factors together to make any kind of map you wanted. And I started doing a lot of those, some of those back in the late 1980s when we were using the Army Corps of Engineers GRASS program. It was the first GIS that was open source government, and so we could actually put as one place for the town of Moraga, we put in 39 different attributes into our GRASS system, and then we actually came up with a development capabilities map based on 7 of those that were most important to the town council, the planning commission, so on and so forth. And so you can actually say to your client, well, what is your greatest concern here? Is it fire danger? Is it erosion? Is it landsliding? Is it debris flows? Is it earthquake-induced shaking intensity? You can actually put a weight to all those things and make a geopolitical map. of those hazards. That's not a hard thing to do. What you have to have is good algorithms to start with that are fairly reliable. Now, in doing that study, I had a few surprises. That was the only site we ever had in California up to that time where we had aerial photo coverage going back 60, 70 years, back to 1928. And I was real excited about seeing the frequency of land slippage on some of these most active slides. And I was sorely disappointed to find out that the slides that had moved in the 20s, 30s, 40s, 50s, 60s, 70s, and 80s, none of them were repeat customers. So if they moved in the 20s, they didn't move again in the 20th century. There was another slide that then moved in the 30s or the 40s or the 50s. So that was a real comeuppance for me. I thought the things were much more frequent than that. But if you think about it from a geologic time scale, that was pretty foolish to think that. I was thinking more like a civil engineer from, runoff. And then when I looked at all the runoff data, there was no repeatability in those patterns either. No two storms had the same antecedent moisture and the same delivery of precipitation. So they were all slide triggers, but they were all different. So I wish it was more simple. If it was simpler, I could have become a structural engineer. So if you like things that are simple, they all in a Betty Crocker cookbook, you need to go into structural engineering. But geotechnical engineering, wow. Takes a lot of multidisciplinary background and a lot of judgment. Just a lot of judgment. So if you don't like thinking, get into something else. This business takes a lot of thinking. All right. Here's a map, landslide hazard map I did, part of one, for the city of Orinda. It was probably the most litigious hunk of real estate in the United States, 9-square-mile town in the San Francisco East Bay. End users are going to demand increasingly detailed assessments. What does that mean? It means they want to look on here and say, where's my property? So that's what I'm showing here. Here's landslides and surficial deposits and the tax assessor's parcel map. That's what people want to see. They don't want to see a topographic map. They want to see, where's my property on here, and did you make it red, yellow, or white? Or brown, some kind of brown, So landslide hazard maps using GIS are going to be overlain on tax assessor parcel maps like this, just like FEMA flood insurance rate maps. And what you're going to end up doing is spreading the risk to lenders and insurers. We have bankrupted our federal flood insurance program. We've spent more money in this country on flood mitigation since 1993 than the entire history of the country since 1776. So just from 93 to present, we spent more money than all the years prior to 1993. So it's out of control right now. What's going to happen in your generation is they're probably going to go to an all-hazard federal insurance program. That's where we're heading. What does that mean? That means everybody's going to be in it. No one's going to get an exclusion. Everybody's going to pay something based on the geohazards in your area. Earthquakes, fires, tornadoes, floods, landslides, all of this stuff is going to come into play, and everybody's going to pay into the pot because we're bankrupting the country right now. But if you look at where everybody's living, over the last 60 years, a greater and greater percentage of the country has moved closer and closer to the coast. I'm the great exception to that. I moved from the coast to here because I wanted to be close to you. But most other folks want to get out of Rolla and go to the coast because people wear less clothes there, I guess. I don't know the reason. But anyway, everybody wants to be by the coast where all the action is. And that's where all the action is. The coast is a heck of a bad place to be when it's raining or the wind's blowing hard because you don't have any protection. So if we look at where money is getting spent, hurricanes are far and away the biggest natural peril that we've seen in the last 100 years to American property, but that's because we've had more and more of the population moving closer and closer to the coast. So right now we have about 60% of the population living within 2 hours of the coast. So we have increasing amount of damage that's associated with the hurricanes. So big problems out there that are going to be challenges for your generation. But geoscientists are going to play a very, very large role in all this, especially when you start putting in sea level rise and the fact that you're going to have to start mitigating sea level rise. Sea level rose 12 inches the last century. And global warming didn't allegedly start until we started burning a lot of fossil fuels in the 1920s onward. It's been increasing. So sea level is probably going to go up 12 inches or more the next century, and that portends a lot of challenges, great challenges in terms of engineering mitigation measures. The future map products are going to look like this. You're going to map landslides, and then you're going to wrap those on digital elevation model, which is wrapped on an aerial photograph off Google Earth, and you can put the towns and the houses over that. You can put the tax assessor's parcel map on it, but people are going to see these kinds of products. This is out of Colorado Geological Survey right now in an ArcGIS 9.1 product. That's what we're going to be seeing on a routine basis. And people are going to be able to go out there and get this information off the internet. It's not going to be hidden in some university library somewhere. It's going to be on the internet. And so it's going to have services. Our services are going to be in great demand for places like this where you say, well, that's a marginal place to build. Can you get me a ski resort right in here? Well, yeah, anything. You can do anything. You've got enough money. But in the old days, one of the hardest things to do was to sell a client on the fact that they needed to do some major amount of investigation and mitigative work. And we're really helped today by these kinds of products that can allow us to go in and say, hey, I'm not being a bad guy to you. That's just what, that's the matter of public record. And the matter of public record says, we got all these different slides out here. Some of these are master's theses. Some are by the State Highway Department. Some are by the Forest Service. They're by all these different people, and we can put them all in this master database, and voila, they're not hidden in the basement anymore. I think that's a pretty important concept to get a hold of. Now, that's great in areas where you have this kind of data. This kind of data only exists in the highly urbanized areas where you're spending the money to do this stuff. It doesn't exist in areas that haven't seen the problem yet. That's always going to plague us. What's the most defendable place in the United States for flood control? Where did modern flood control engineering start? Was it in Los Angeles? No. It was 1913 in Dayton, Ohio, where the Miami River had a flood, and it killed about 400 children. And the city fathers in Miami and in Dayton, Ohio said, we don't ever want to have this happen again. Get us the most conservative engineer you can find. They found a guy named Arthur Morgan. He came up from Memphis, and Morgan tore out 25% of downtown Dayton. Tore it down. Because they had encroached the river and encroached the river and encroached the river, and pretty soon they didn't have a 10-year channel. He then built 3 of the largest dams in America up to that time. The 3 largest dams prior to World War I, Germantown being the largest one. And all those dams were huge earthen dams with big, huge slots made out of concrete right down the middle. What are those? They're flood retention basins. And everybody said, what a colossal waste of money. You're building these huge dams. And no largemouth bass fishing. No recreation. No power development. And he said, if I allow water to be stored in those dams, you know what'll happen? Yeah, it'll be economic bliss. We'll make money. It'll be good for the economy. It'll pay for the project. That's a good idea. We want to pay for the project with the sale of electricity and the recreational use and blah, 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 blah. And Morgan goes, no. What'll happen is, every year you make money, you'll figure out a way to raise the lake a little higher so you make a little more money. And after you do that for a couple of years, you'll raise it a little higher to make even a little more money. Because the people in charge of it will like the money, because money corrupts people. And pretty soon, the project you built for flood control won't be controlling floods anymore. It'll be multi-use. Multi-use means many ways of making money. And the flood storage will be gone. And it'll be flushed out because you'll keep shopping around till you find consultants. Because some consultants will say anything for $500. This is in 1913. Don't you love this? He was right. And fortunately, he won out. He then went into Pueblo, Colorado after the 1922 flood in Colorado, did the same thing there. And in January 1st, 1997, California, we had $30 billion in flood damage in the state that has the most flood control engineering and most reservoirs of any state in the United States. 8,000 reservoirs, including some of the world's largest, like the world's highest Rockville Dam till a few years ago, Oroville Dam, 869 feet high, built by the state of California, not even a federal project. And they had over $1.9 billion of damage just downstream of Oroville Dam, which was there to protect Marysville and Yuba City and Sacramento. What happened? Well, I read Arthur Morgan's book when I went up to Sacramento to testify. And that's exactly what happened in California. They allowed multiple use reservoirs, and what happened to the flood storage? Well, they shopped around, and they found consultants. And they kept shopping around until they found consultants that said, well, we need to write a new computer program for you. We have computers now. They didn't have computers, 20 years ago, and we're smarter now. Every generation thinks it's smarter than the previous generation. And that there's nothing they could learn from somebody 2 generations ago, more than 40 years ago. There's old fogies, right? And so they wrote all these models, and they modernized everything, and they had computer controlled. Oh, computer control. That's what was controlling Tom Sauk Upper Reservoir. First computer-controlled project in the United States. They didn't have to have anybody up there watching the level of the lake to see if it spilled over. They had computerized control. What could go wrong? Everything. Does anything ever go wrong with your computer? Ever? You're laughing. Something I don't know? Anyway, here's what happened in California. That storm on January 1st, 97 was 6 degrees warmer than any previous storm that had hit California on New Year's Day. So they got a tremendous amount of coincident melting. So they had a storm that came in and dumped, upwards of 30 inches of rain over a 3-day period, and they had about 18 inches of coincident melting. So they had a net runoff event of 50 inches, and their models were maxed out for 35. So they overwhelmed their flood storage. And that's the flood storage that they had moved things down to. So here they had all these people who put mobile homes in next to the river. Everybody wants to be by the river, by the water. People wear less clothes there, So they were all by the river, and all of a sudden these dams that had never spilled before all spilled and wiped out. And then everybody got mad. Everybody started suing. Oh, the attorneys were having a feeding fest. They were having a great time until they looked at the contracts. And all these people had contracts. And in the fine, you ever bothered to read the fine print on the? You don't ever want to do that. It's depressing. It really is. And you read the fine print there, and it said, in the event, that there's a big, huge storm, we may have to dump a whole bunch of water here, and the undersigned acknowledges that they may get their ass blown out of the floodplain and lose everything, but please sign here, thank you. It's there in the fine print. Ouch. Ouch. Boy, Morgan knew people. He had them dialed in right. Abraham Lincoln said, greatest test of a man's integrity is give him power, because power tends to corrupt. Sad but true. All right. Well, that's all I have for today. We'll be heading. We want you to finish writing assignment 3 on the Walmart, and then we'll be moving on into chapter 8. In chapter 8, is the one that's on hydrology, fluvial processes. Oh, by the way, I posted today, somebody sent me from the distance class, the 46-page paper by Skip Hendren and Frank Patton on the Vaillant slide. So I posted this on the Blackboard site under documents. This is a great article to have on Vaillant, and I have a smaller article on Vaillant and another smaller article on St. Francis Dam if you're interested in that, which I put on the website. That's all. Thank you. If you have homework to turn in, please turn it in.